أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. In today's lecture we will discuss magnetism and nanomaterial. In previous lecture we have also discussed magnetism, but that was actually the atomic origin of the magnetism, the division of magnetic material based on the magnetic moment and based on their magnetic properties, and some other basic understanding about magnetic materials. So today we are moving toward the magnetism and nanomaterial, and want to study the same topic in more in a broad sense. So if we see, magnetic property arise due to the magnetic moments, and the magnetic moments arise due to the unpaired electron present in the atoms. The unpaired electron, the electron that are revolving around the nucleus, create spin and orbital magnetic moment, which contribute to the total magnetic moment if if there are some unpaired electrons. So there is some intrinsic magnetic moment for some of the materials. So that was actually ferromagnetic material we discussed in the previous lecture in detail. So it was actually the property of the material that they have some intrinsic magnetic properties due to the unpaired electrons. So today we are going to discuss why the magnetic properties of bulk material are different from the magnetic properties of the nanomaterial. This is actually the magnetic nanostructures. First you need to know the magnetic nanostructure in bulk materials. So if we consider bulk magnetic materials, some structures can be in the nanoscale, just like we consider the domain walls that are actually in nanoscale, and in a ferromagnetic material the domain walls are around 60 nanometer for Fe or iron. So this is definitely in nanoscale. So some domain walls, especially those in the vicinity of the surface or grand boundaries, could themselves be in nano size. So spin clusters are also in nano size, and that is above paramagnetic Curie temperature. That is also in the nanoscale. So when we discuss or when we go from bulk to nano, only the structure sensitive magnetic property like coercivity is expected to change significantly. So some of the possibility when we go from the bulk of a material toward the nano size material, what property should we expect to change? One is the ferromagnetic particles becoming single domains, the super paramagnetism in small ferromagnetic particles, that is actually particles which are ferromagnetic in bulk. We have gained magnetoresistance effect in hybrids, they are actually in layer structures, and antiferromagnetic particles in bulk behaving like ferromagnets. We have dependence of magnetic materials on the dimensionality of the systems. Means how the magnetic property of the material change with the dimension of the particular systems. So there is an increase in magnetic moment or atom as we decrease the dimensionality of the atoms. How? This is actually the indicator of fundamental difference in magnetic behavior between nanostructure and bulk materials. So this effect is all the more noteworthy as surface spins are usually not ordered along the same direction as the spin in the interior of the material. So how we can expect, and we can see here in this table how it is compared, just like for nickel and ferrum. We have the bulk as well as a nanoscale in 0 dimensional, 1 dimensional and 2 dimensional. So the magnetic moment is described in mu b per atom. So we see the change in value. For 0 dimension it is higher, that is 2, but coming toward the same material at 1 dimension it become 1.1, and further reduction has been found in 2 dimension where it is 0.68. and if we investigate the same thing in bulk, it becomes 0.56 with a further reduction. Similarly, if we consider for Fe, so at 0 dimension its magnetic moment per atom is 4.0. With the increase in dimensionality would happen, its magnetic moment per atom reduce greatly and it becomes 3.3 for one dimensional, 2.96 for two dimensional, and 2.27 for bulk materials. So here we can see that increase in magnetic moment atoms is found with the decrease in the dimensionality of the systems. So this is the general illustration from this table. So if we can have a maximum possible magnetic moments of 6 mu b per atom, that is actually 3 mu b from the orbital moments and 3 mu b from the spin moments, and this implies that is in 0 dimension nanocrystal very little of the orbital magnetic moment is quenched. So what is the phenomena of super paramagnetism and how it occurs in nanomaterials? As the size of the particle is reduced, would happen the whole particle become a single domain, but there is a critical size for it. I mean, it become a single domain below a particular critical size. So this aspect can be understood in two particular ways. The first one is a particle smaller than the domain wall thickness cannot sustain a domain wall. That is noting that domain wall thickness may not be constant with 0. And the other is the magnetostatic energy increases as r cube. R is being the radius of the particle and the domain wall energy is a function of r square. So there must be a critical radius below which domain walls are not stable. So this is actually the general trend for that, and the ratio is just like RC is F into sigma divided by m square, where RC is the magnetic moment per unit mass. So here we can compare the particle diameter with the intrinsic corrosivity, and that is the log of intrinsic corrosivity, and we can see how we can find the super paramagnetic effect. That is actually the thermal disordering effect dominate or tendency for spin alignment, and this particular curve shows the thermal disordering effect due to the temperature which disorder. So here we have single domain wall rotation, and here we have multi-domain wall rotation, but this is the curve how it can be shown that in case of multi-domain there is increasing corrosivity with decreasing temperature. If we see the multi-domain walls, then by looking at the curve we can find that there is increasing corrosivity with decreasing size, with the decreasing particle size. But would happen if we have single domain instead of the multi-domain, so what happen, we can get the peak corrosivity, and there is decreasing corrosivity with decreasing particle size. In case of single domain there is decreasing corrosivity with decreasing particle size, so there is direct relationship between the. So if we compare here in this particular case these values, it is clearly shown how the corrosivity change with the particle size. So comparison between paramagnetism and super paramagnetism. So how we can compare the two with each other? If we have magnetization of oxygen, that is mu is 2.8 mu b per molecule, so in that case it is equal to 2.64 multiplied by 10 to the power minus 23 ampere square divided by a molecule. So this is actually number of oxygen molecules is the Avogadro number, that is 6.023 multiplied by 10 to the power 23 and per 0.032 per kg. So magnetic field applied, that the external magnetic field is equal to 20 multiplied by 10 to the power 6 A divided by m, and similarly corrosivity at 20 degrees centigrade is 1.36 multiplied by 10 to the power minus 6. So what will be the magnetization effect of this strong field? So we can do the calculation for it because we have already the equation. So just putting the value, we can get the value, we can get the magnetization effect due to this strong field, and that will be caused by putting the value in this equation. So here sigma is equal to xmh, so we can get the value in this equation, and we can get the percentage of possible magnetization is around 5.5%. So even it is concluded that strong fields are very poor in aligning the magnetic moments of paramagnetic materials. If we consider the paramagnetic material and we apply this, we increase the strength of magnetic fields, so even strong fields are poor, are less effective in aligning the magnetic moments. When so we have another example regarding the crystal structure, but that is that if you consider an iron nanoparticles, so we need to calculate the magnetization if the diameter of the particle is d is equal to particle size is 15 nanometer and it is saturated at UF is equal to 2.2 μb. So how we can calculate the volume of the particle is this, and volume per atom in BCC Fc, if we consider that the crystal structure is basis Fe, so it will have this volume, so we can get this volume. So number of atoms of Fe in the particle is this amount, so we can multiply by this. So magnetic moment of particle under saturation is just multiply the total number of atom by the saturation magnetization, so it is equal to 3 μb, that is a Bohr magneton. So further we can get this magnitude of magnetic saturation magnetization of this Bohr magneton at 3 μb. This is something regarding the change in size, the change in magnetic property. Here we see that change in size lead to the change in structure, and then further lead to the change in mechanism, leading to the change in property of the material, and finally lead to the, when the property of the material is changed, then it lead to the change in the performance of material. This is the general schematic shows that describes how the properties of the material are changed indirectly with the change in the particle size. So that is a stepwise change leading to the final property and at the end the performance of the materials. So if we change the structure of the material, definitely the property of the material will change. If we change the structure of the material, the property of the material are changed, and as a result the performance of the material will also change. Coming toward the B or the second row, if we change the size, particle size, it will lead to the change in the mechanism, and further leading toward the change in the property of the material, and the final end, when the property of the material is changed, it will lead to the change in the performance of the material. And change in size in the third categories lead to the change in property. This is the final end, and in which change in property directly lead to the change in performance of the material. And the final end that is really interesting for us, and that is actually called as a quantum effect, that change in size leads to the change in the performance of the material. And there is direct relationship. In that case there were indirect relationship, but this is a direct relationship showing that change in size of the particle lead to the change in performance of the material. So this is that criteria, that reduction in size, change in the domain structure, change in the mechanism of magnetization, that is the super paramagnetism, and that change the property like corrosivity and retentivity, and finally the performance of the material is greatly influenced. So how we have magnetic clusters and how we can describe the magnetic cluster. So like other property of cluster, magnetic properties of clusters can change with the addition or removal of atoms. So clusters are actually few to are number of atoms that are few to thousands of atoms, typically extended about 5 nanometer. So important factor which determine the magnetic behavior of clusters are the atomic structure. The second one is the nearest neighbors distance, that is the coordination number actually, and the third one is the purity and defect structure of that particular clusters. We have ferromagnetic clusters, and how we can describe the property of the ferromagnetic cluster. Ferromagnetic clusters are actually if we consider small cluster whose dimension is whose size is less than 20 atoms, so there are large oscillation in the magnetic moments of the cluster, that is calculated as a magnetic moment per atom. So for more than 600 atoms in the cluster, that is actually bulk like behavior emerging. With increasing number of atoms, the oscillation dies down and bulk behavior emerges. So just like iron can have a maximum possible moments of 6 μb per atom, just like if we consider iron 12, so the cluster has a moment of 5.4 μb per atom. So in iron 13 it is 2.44 μb, while in crystal nickel 13 cluster has abnormally low temperature, as well as this is attributed to the isohedral structure of the clusters, which is densely packed. So this is some of the property of the ferromagnetic clusters. So we have antiferromagnetic clusters as well. I mean, if we change the antiferromagnetic materials, so the clusters are antiferromagnetic cluster, but in this case we do not expect any magnetic moments in the bulk. However, there is a possibility that the in small clusters up spins do not cancel out the down spin. I mean, the up spins is not cancelled by the down spin, so it lead to a net magnetic moment. So these are antiferromagnetic behaviors as a ferromagnet. So these are actually called as antiferromagnetic materials. So what happen in this material, magnetic frustrations is also a possibility. That is actually the spin on a given atom does not know which way to point. So if we consider small cluster of chromium, that is one of the few metal which are antiferromagnetic, so it have an interesting rich set of possibility. So a plot of magnetic moment per atom oscillation with size as the case of clusters describe that. So it means we can describe the clusters oscillation with that. So if we consider the manganese structure Mn cluster, then it shows similarity with ferromagnetic Fe clusters with regard to the cluster size dependence. So experimental production, how we can experimentally produce the crystal and cluster, and what is the way to produce this. So is actually the example of metal vapor production method, where a gas phase supersaturated metal vapor is ejected into the where ejected into flowing inert gas. Yes, the gas is ejected into the flowing inert gas, which is cooled, and what happen, the metal vapor is produced with the help of thermal evaporation, laser ablation, and sputtering. So what happen, most mass separators requires the clusters to be charged. The clusters need to be ionized if they are not charged. So example of mass filters include radio frequency quadrupole filter, Van filters, and some other example as well. So what happen, at the end of separation we can get a narrow distribution of masses of particles. In the small clusters we can even get a precise number of atoms in the clusters. So measurement of magnetic moments of clusters. So how we can measure the magnetic moment of cluster? The experimental results presented for free clusters, that is especially the Fe, Cr, and Mn, they are typically measured using a setup which is based on the Stunga law experiment we already studied in the modern physics. So what happened in this experiment, a collimated cluster beam is guided into a magnetic field that is non-uniform magnetic field. The field gradient will deflect a cluster with magnetic moment by a distance d given by the equation as below. So what happened? For cluster deposited on surface, other techniques of measurement exist, such as X-ray magnetic and some other method. So if we can consider the embedded cluster technique like microsquid measurement, that can also be used for that measurement. So we have experimental clusters, experimental setup for the measurement of magnetic moment. This is how the magnetic moments are measured stepwise with the help of this method. So still we have some problem regarding the measurement of magnetic moment of nanomaterial, because it is really very complicated study, and that is at nanoscale. So the measurement of magnetic properties of cluster nano is needless, is actually a challenging process. So what happened in clusters, the magnetic moment is a sensitive function of the number of atoms in the cluster. That is actually the number of atoms to be known precisely, but it is not very sure to us. We are unable to precisely know the number of atoms. There is some other contamination. There might be some contamination that affect the values. Temperature also affect, and that play a key role in the magnetic behavior of at nanoscale. We have spin alignment in nanoscale systems that could be very different from their bulk counterpart, and hence models with different with which experimental results are compared. So in case of particle and a substrate are embedded magnetic particle, the role of the interface of the substrate could be pronounced. So this is some of the problem we are facing when we are dealing with the measurement of magnetic properties of nanomaterials. So this is some of the magnetism in thin films or the hybrid. So and its variation with the with T for the 2D versus 3D behavior. So in this system, nickel films are considered on copper substrate, copper 110 substrate. So we can draw the curve between that like this. So we can calculate the Curie temperature for that, for the thin films, and that is actually the transition temperature for that particular gas. So we have magnetism of hybrids, that is GAN, that is actually called as GAN magnetoresistance, GMR effect, and that is compared to the normal conventional magnetoresistance, where the change in resistance due to magnetic field is 5%, around 5% in GMR. So the change could be of the order of 80% or more. So this is some of the property of the GMR, because it has interesting application, and that is widely used in various applications. So we have magnetism and hybrids material, that is exchange anisotropy due to the exchange coupling of spin across an interface between ferromagnetic phase and antiferromagnetic phase. So some steps are involved for creating the exchange anisotropy, that is actually need single domain. So we need to apply field above the Néel temperature, and we need to cool the system below the Néel temperature of the FM phase to introduce professional alignment, and finally we need to construct the usual MH loop. So if we consider that the field is removed, if the field is removed, the spin in the FM phase will flick to the field cool orientation. So that will affect the FM phase. So this is some of the alignment of the magnetic moment in different. We can change the alignment by changing the direction of field, and this is some of the application of H will change their properties for ferromagnetic. So we have some other application where we can use nano disk. We can store data, and that is for some of the application of the magnetic nanoparticle. magnetism, where we have 15 nanometer thick pomalite disc shows the vortex that the diameter of the disc is about 100 diameter. So this can have use for special type of applications. So we have nano rings, that is also rings from the magnetic moment arranged in a different order, and that is used for special application. So this is something about the magnetic properties in nanomaterial and in nano particles. So this was actually regarding the magnetic properties of materials. So thank you very much for now.